Let's see, where are we at now in this class? Can't remember what we did last time. We're in chapter 4, is that what we're doing? Data analysis. We're doing manipulating matrices. We did that already. We did chapter 4 already. I think, yeah, we did chapter 4. So we're on chapter 5. Chapter 5, we're going to be plotting some stuff. So this finally starts to get a little bit more interesting. And that's good. So let's take a look at this. I'm in the wrong place. Let's go to MATLAB. Excuse me. Okay, so chapter 5, MATLAB is where we're at today. We're starting on chapter 149, or on page 149 it looks like, with two-dimensional plots. And I'm going to clear some things out here. Get rid of some junk. Okay, so starting fresh. Remember that you need to take your notes in an M file along, the code that we write, along with any notes that you have as comment lines, and turn those in at the beginning of your homework. Also remember that you are responsible to participate in the shared document. We've now gotten through kind of the basics of MATLAB, so I will probably start taking a look at what homework has been turned in. I usually wait a little while because my students that are at different places and watching the videos at different times are kind of doing things in a different time schedule. But I will start looking at what has been turned in and start grading it. Remember that the grading rubrics are in Blackboard, so you can kind of see what you're graded for. Usually it's about half content and the other half is about, half is participation, about the other half is content and how it's presented, how well it works, and everything else like that. So make sure that you're doing your assignments accordingly. And at this point you really want to try to be caught up as much as possible, because I will start grading. And like I said, I try to grade a little bit behind the work just because I'm waiting for things to come in from people that are watching the videos at different times. But as we get closer and closer to the end of the semester, I'm expecting everybody to be more and more on task and on the same schedule. So I'm going to try to grade more regularly with the assignments. But I will grade the first few assignments hopefully this coming weekend or next week, and then try to be a week or two behind so that you can see kind of what's going on. But at any time, if you have any questions about what you're doing and you're not sure if it's going out right, send me your M file. Send me an email and say, hey, can you take a look at this program, see what's going on? Because we will be getting into parts here that are more complicated, a little harder to understand how to fix the code that you're writing or to make it work or whatever else. So at any time, send me an email and I'll be happy to look at it and help you out. Okay, so we're going to start off with two-dimensional plots, simple stuff to begin with. So the first thing we're going to do is we're going to create some arrays. We'll start off with an array of x values. And, oh yes, let me put it up, sorry. Put this up on the screen in the room here. Okay, so we'll start off by just making a simple array of numbers between 2 and 18, or 0 and 18, spaced two numbers apart. So all the even numbers, essentially. 0, we do a 0, semicolon, a 2, a semicolon, or not a semicolon, a colon, and an 18. And that'll give us the array of numbers that we want, and I'm going to suppress the output. Oops. I did that wrong. It shouldn't be 02318, it should be 0218. So it gave me And the reason I knew something was wrong right away is I looked over here at my workspace and I saw that there was a value of 0. There was nothing in this array. This array is empty because I went in steps of 23 to 18, so it took 23 steps and 18 was already passed. I didn't put anything in there. So I'm going to redo that. Instead of 23 to 18, I'm going to go 0, 2 to 18, hit enter, and now I've got the proper array over here in my workspace. That's what I'm looking for. And then I'm going to do some y values. I'm going to do y equals, and I'm just going to give some values here that they put in for us. So it's an array of numbers that looks like this. The first number is 0, and then the second number is 0.33, the third number is 4.13, fourth number is 6.29, and onward, 6.85, and 11.19. The numbers aren't all that important, but I'm going to try to do it the way they're doing it here. 13.96 and 16.33. So these two arrays, oh, one more, 18.17. There we go. These two arrays should have the same number of elements if we're going to use them to plot something. So let's check to see if they have the same number of elements, x. If I go over here and I click on it, let's see, why doesn't it give me the, usually when you just float your thing over it, it tells you what it is. Let's just click on it and open it up. It's a 1 by 10 double, so that's good. Close that one. I'll open up the second one. It's also a 1 by 10 double. So it's 1 row, 10 columns, and we've got 2 that have the same number of elements. I could also go ahead and make a new array that shows that these things have it. I could do x and put the little what do they call that? They call that the, not inverse, but the, anyway, it flips the columns for the rows, so it's going to make a big column. And then I could do a comma y with the same thing, little quote mark there. And that should give me 2 columns of numbers, the column of x's and the column of y's, right? And you can see that they have the same number, and that's great. In this particular case, they're calling this first one time and this second one distance, and that's fine, whatever. Let's just plot it now. Let's plot. We're just going to use the function called plot. We're going to plot xy. It's really simple. If you plot xy, it will bring up a figure window, and the figure window will show a plot of this. And the default plot is a line plot that draws a straight line from point to point using the first first vector that you put in of numbers as the x values, the second one is the y values, and you're good to go. And it's really quite a simple thing to do, not hard to figure out, not hard to make it work. Some things that you can do with this window, there's a little arrow up here that's on the right upper corner. If you click that arrow, it will allow you to dock this plot or put the plot inside of your normal windows, which is kind of nice. And then you can actually rearrange it. You can actually put this plot window somewhere else if you want to. I could put my plot window right up here, for example. If I wanted to, I can grab it and I can put it down here, or I could grab it, I could put it over here or over here. So it can put it in as a tab, it can put it in as another window, as a separate window. I can put it right there, for example. There's lots of ways you can do that. If you close it, it'll just revert back to where you were before. So that's no big deal. So you can dock your plot windows, and if you close them, they'll be gone. And you'll have to find them again. But that's just a very simple plot, no big deal. But you're also able to do other things. For example, you're able to label the axes. So if I do use the function xLabel, and I want that tells me what I want to label the x-axis as, and I have to put in quote marks because this is going to be a string. It's going to be a string, what we call a string of letters or a string of characters or a word. So I do time, and then I'm going to do comma in seconds, or I could do parentheses in seconds, which is normally what you see, and then I have to close that with a single quote. Right? And if I do an X label like that and hit, oops, I put too many things at the end of that. If I do an X label like that, then the next time a plot comes up, the X axis will be labeled with time seconds. Now, I haven't told it to plot X and Y again, because every time I close a plot, it resets the figure window. If you leave the figure window open and you do a new plot, it'll just give you a new figure window. So what I'm going to do is I'm going to do X label, time, seconds, and I'm going to do, let's do X label, time, seconds, and then I'm going to do, what I want to do. Oof. I think that I actually want to, let's plot first. So I'm going to go up and do my plot first, and then I'm going to do my X label, time in seconds, and then I'm going to go back to my figure window, which is here somewhere. It's over here, and it's put that label on there, and then I can do the Y label, label the Y axis, do Y label with, I'll call it distance in meters. Hit return, and if I go back to my figure window, which is right here, it has labeled the Y-axis now. So it does that in real time. And there you have a very nice thing. You can also give it a title. I think it's just title. Can't remember, we'll find out here real soon. We'll call it, it's just title. We'll call it lab test or something like that. Put that on there and open up our figure window. And it's put the title at the top, lab test, which is really nice. Now this figure can now be saved. If I come up here and I save it, it can be saved, and you can save it as a MATLAB figure, or a bitmap file, or a JPEG image, or anything else, a TIFF image, a document format PDF, so that you can take it into other things and use it in a presentation, or you can use it in a paper or something like that. Very nice little feature that you can export that very cleanly and very, very quickly to something else. You can also print it directly from here. You can also add things to it. You can add colors. You can essentially you can add a data cursor. So if I put a data cursor on here, I can actually look at pieces of data on the graph, different points on the graph, and so on and so forth. So I think this has to be dragged once you put it on here. Can't remember. But anyway, you can do all kinds of things up here with these tools. You can make links to it on the internet and everything else. So lots of cool stuff you can do with that once you have plotted something. Okay, let's see, what else do we want to do? Oh yeah. Excuse me. Let's go up here to our M file and let's do some plotting from the M file. So let's create let's see if I can remember how to do this. With code. Editor. See if I can't remember all of a sudden how to do this. Do help cell. So we want to create, I don't want to create a cell array, I want to use cell mode. Can't remember how to use cell mode. It's not in breakpoints. It's not what I want. It's in, I thought it was over here in the navigate stuff. Can't fight there. That's okay. It's not that important. They want to use cell. If you remember, this is something that was new to MATLAB to me recently, where you create different cells within your M file. If you remember how to do cells in an M file, you can go ahead and use this, and then you can create multiple plots in different cells. Or you can do what I learned to do, which is just to use the pause, which is fine. So let's go ahead and do that. Let's go ahead and put in our X. I'm going to go down here to my command window. I'm going to copy my X, copy that, put it up here. And I'm going to copy my Y, put that up here, paste. And then I'm going to plot this. So I'm going to copy my commands down here. If I plot X, Y, and then I label it, copy that and put it in here, paste, and then I label my Y-axis and give it a title. Copy that, put it up here. Then I've got a nice little bit of code up here where I've created my X, I've created my Y, I've got a plot X label, Y label. I could do some comment lines up here to tell what I'm doing, whatever it is I'm doing, plotting 2D plots, whatever, date, time, whatever you want to put up there. And I could comment out here and tell people what I'm doing, tell myself what I'm doing if I don't know what I'm doing. Then I get down here to a point where I could pause it before I move on. Go ahead and pause that, and that'll pause until the user hits the next button. That's my personal favorite way to move on to the next thing. But remember that when you plot something, you are creating these little figure windows, which I don't have anymore. So let's go down here and create one again. If I go here and I plot, I create this figure window, and this one is called figure 1, but MATLAB can open multiple figure windows. It can open figure 2, figure 3, whatever else, and you can actually decide which window to put plots into. You can actually put multiple plots into multiple windows. So let's go ahead and try that really quick. I've got in my thing here, I've got, let's see here. Where are they doing it? Okay. So coming down here, if I do this figure 2, so I just use the command called figure and 2, it'll open a new figure window so that when I open a new plot, it'll put it in that new figure window. So you can choose to put it in new figure windows, or you can actually use some different commands to do different things. So here's another example. Let's actually do the one in the book here. This is not a bad one. X equals 0. We're going to go from 0 in steps of pi over 100. So we're going to go 0 pi divided by 100. And we're going to go all the way up to 2 pi, I think. So 2 times pi looks like. 2 times pi. That's going to be our x values. And our y values, we're going to actually calculate something from our x's. So we're going to use y1 since we've already used y. The y1 will equal x cosine of x, for example. Let's do cosine of 4x. Now we'll just do cosine of x. So this is cosine of x, and then we're going to go ahead and plot these two things. We're going to plot x and y1. Right? Let's see where this ends up. We've got two figure windows. There's figure 2. Since I chose figure 2 before I made this new plot, that's where I put this new plot. Figure 1 is still here, right? If I go ahead and I choose figure 1, and then I go that previous plot here, I think it should put it into figure 1. So let's try that out. Make sure that I did it right. And I go back now to figure 1, and it's put my plot of the cosine into figure 1 now. So it erased the previous figure. Now there's something else I can do. Now I can actually put in something called hold, and you just do hold and then on. You don't have to put in parentheses. But this actually is going to hold whatever the last plot was in the last figure window was put into. So it was put into figure 1, and it was the plot of the cosine, and I'm going to hold that. It's going to stay there, and I'm going to make a new plot. I'm going to make y2 is going to equal, y2 will equal cosine of, let's just do the cosine of x instead of the cosine of 4x. And let's see what it gives us. So y2 equals the cosine of x. I'm going to put that in to, I'm going to put the plot of x comma y2 into figure 1. It's just going to go into it since that was the last one I used. And I'm going to open up figure 1. Whoa. Should have gone into there. Apparently it did not. I don't know why. Oh, because I put the hold on in the wrong place. Okay. So let's do our plot of x1, y1 again. So I do my plot of x1, y1, and then I put my, I've got my new x's and y's in, and then I plot x1, y2. No, then I do my hold on. And then I plot x1, y2. That's what should do it. Order matters, but it's still not doing it. Why is it still not doing it? Let's close everything. I'm going to close my figures and see if I can do this. Okay. So now we're going to do this again. What's my x? Put in my x. There's my x. Do my y. 1. There's y1. Cosine. Oh, that's why. I want y1 to be cosine 4x. I just did cosine x before, so I was just doing them on top of each other. That's why it was different. Okay, so now I'm going to do my plot of x and y1 right there. So there's my plot of x and y1 with 4 times x. And then I'm going to put the plot, then I'm going to do y2, which is just cosine x. And then I'm going to plot then I'm going to put my hold on, actually. Put in hold on. And then I'm going to plot it, my y2, and then I'm going to look at my window. So what I was doing last time I was plotting the same thing on top of the same thing, which is why it changed color, but it didn't change shape. So this one has 2 different things plotted right on top of each other, where you plot the first one, and then you create the second, you put the hold on, and then you create the second one and plot the second one. And it'll put it right on top of the last one that you plotted. And you can do this as many times as you want while the hold is on, because the hold is just on until you turn it off. If I do this for another one and I do y3 equals, for example, instead of, we'll make it equal to 5 times cosine of x. That's a good one. Do that one, and then I plot y3 with x. Then I go back to my figure. You can see that it plots another thing on top. The original 2 are the blue and then the red, and then the next one is the yellow, right? And you can plot as many things on top of each other as you want. You could get really crazy and start plotting really strange things like y4, y43 we'll call it, equals 15 times cosine, no, we'll do 15 negative 15. Instead of cosine, we'll do the sine. We'll do the sine of the cosine. Why not? Of x squared minus x thirds or something like this. You can get really crazy with it if you want. And then you can divide the whole thing by x. Why not? You can just be as crazy as you want to, hit enter, It doesn't like that because I'm using the dot. I need to use a dot squared here. Oops, I need to go up again here. So here's my last thing. I need to do a dot divide. I need to do a dot squared. And I need to do the sine of the cosine of x. There we go. That's more correct, but we have too many parentheses there, looks like. Okay. And then we can, oh, no, we didn't have too many. No, that's fine. That'll work. So we erase that, hit return, go to our figure, and you can get all kinds of crazy stuff going on. I don't know where that last one ended up. It looks like it's not on the graph. Oh, we didn't plot it. Got to plot it still. So we'll plot this in Y43. And then we'll go look at our graph. And that's what it looks like now. So this last one is this purple one. And every time it plots a new thing, it'll give you a new color. And the colors come in order unless you choose them specifically. Unless you choose them specifically, the colors will come in this specific order every time. It'll go blue, then red, kind of reddish brown, then yellow, then purple, and then it goes on and on and on through this very specific order of colors. After it runs out of those specific order of colors, it will actually use different textures of the line, I think, or something like that. But anyway, that is that. There are also special plots that you can put in. One that they really like in MATLAB is called this one, plot peaks. So this one is a saved function in MATLAB that MATLAB knows how to plot. Go ahead and hit it, and it gives you this right here. And another tool that you can use is this tool up here, which is the manipulation tool, which allows you to manipulate the graph in 3 dimensions. So you can look at it from different angles. You can start to look at it in different dimensions, if it is a 3-dimensional graph, which this one is. So that's kind of a useful tool, especially in the 3-dimensional graphs. So this is actually the function that MATLAB's logo comes from. MATLAB's logo is part of this function. It's this part and this part right here. You may recognize it right there. So that's why they like that function. You can also choose to plot peaks with different numbers of points. So if you do like 100 here, you do peaks and then parentheses 100 and plot it. And you can do plot peaks 1,000. And you get more points. It becomes more dense with the number of points that it graphs here, so that you get a higher resolution imagery essentially. In this point, you might want to zoom in to see things. Come on, zoom in, so that you can see the individual numbers of lines that they've actually plotted. This one has 1,000 lines. It's using 1,000 points in the arrays. So it gets quite interesting as you get in close. So that is all of that. We're going to skip the next part of the chapter, the next part of this chapter, which is the plots of complex arrays, because we're not going to expect you to work with complex numbers. But we will go ahead and set the next part, which is changing line color and mark style. So we're going to teach you how you can manipulate the colors of things and different things on the plots. And then we'll move on to actually plotting some things. You're doing some examples of plotting here. Now in this chapter, I'm trying to remember if we go through the whole chapter, and I'm going to look online to see if that's the case, because I can't remember. I don't think we do. We might, but I think we might save some of the 3-dimensional plotting for next week. So let's take a look. Okay. So this must be week 5 or something like this. That's not where I'm supposed to go. That's where I'm supposed to go. Week 5, I believe. Yeah, so in week 5 we do some very simple plots to start with. At the end we're not really doing, well actually no, that's not true. At the end we're doing 3-dimensional plots and animation, so that's great. We're going all the way through chapter 5 today. Let's just check to make sure that's correct by looking at week 6, because week 6 should be functions then. Let's take a look. Make sure we're not doing another week of plots here. Yep, so week 6 is functions. So we're slowly getting towards the part where we're actually going to build programs. Next week we will be building programs. So that should get a little more interesting for us. So plots this week, we're just going to cover all the plots. So like I said before, you can change colors of plots, the plot lines. You can do a lot of stuff to kind of doctor up these things and change them how you want to do, how you want them to go. One way to figure out how to do this is to use the help function, help plot. And they give you a fair amount of information here for the help function. It's a lot. Start it up here, it gives you 1 full page, 2 full pages of information, and a whole bunch of references. And in this information, they give you information on how to do multiple plots, how to change the color of plots, how to change the plot styles, all kinds of things that you can do. And you can see here that it will accept many, many, many plots into one command for plot. MATLAB is capable of using one command to plot many, many, many things. And you can also use all these different colors, blue, green, red, cyan, magenta, yellow, black, and white. There are more than that as well, but these are the basic ones. And then there are all different kinds of symbols you can put on your plots to mark things, to mark points on a plot. Points and circles and X's and pluses and stars and squares and so on and so forth. All these different shapes that you can put onto your plot to delineate things. So, and you can also put text on your plot in the form of titles and labels and other things like this. And they have all this stuff here. But they also have different kinds of plots that you can do. So they show you all the different kinds of plots that you can do. Scatter plots and semi-log plots and all kinds of plots. So all kinds of things that you can do if you just say help plot. Let's practice doing a couple of these things. So let's do another example here where we're going to start off with just a simple array of numbers from 1 to 10. X is equal to 1, 1 to 10. Oops, didn't want that to print, but that's okay. And Y is just going to be a set of numbers so Y is just going to be a set of numbers between 1 and 10. I'm going to just put in some random numbers. I know that's not what they did here, but that's what I'm going to do. I'm going to just do 1, 12, 3, 5, 23, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do I do? Well, let's do 3. That's fine. So just random numbers here. And then we're going to plot x, y, x comma y. Now if we plot just x and y, all we get is this plain plot here. No titles, no labels. It plots in blue because that's the standard. I'm going to close that out. And I'm going to plot let's see. I'm going to plot it a little differently here. I'm going to do a plot of x, y actually. But now I'm going to add an extra command. The extra command is going to be this. So I put in quotes, a 0, a K, and then I put a little thing in front of it there, a little colon. And then I'm going to close the quote. So these two commands, O and K, have meanings. And those meanings are in the table on page 157, but they're also in the help thing up here. So if I go up here to K, for example, K means that I'm going to give it to give this line a particular color. Here's the table right here. K is a particular color. It's black, so I'm going to change the color to black. The O is a particular marker. It's the circle, right? And the colon means it's going to be a dotted line. So I should get a dotted line. The points should be marked with circles, and I should get a black line. Let's see what happens. So I've done dotted line, circles, black is what that hopefully should give us. Hit return, and the connecting lines is now a dotted line. That's from the little colon. Each point that it actually plots is a circle on it now. That's from the O in there, and then it's turned it black. And you can choose any of these things that you want to in that order. So the line types, you have solid, dotted, dash lines, and dash dot and dash lines. You have for point type, you have points, circles, X marks, plus marks, stars, whatever else. And for color, you have blue, green, red, cyan, magenta, and so on. And you can do them all you want. And you can do multiple plots this way as well. So I'm going to put multiple plots on this one thing by creating some more Y's. I'm going to use the same X's, but I'm going to create some more Y's. So this next Y is going to equal, we'll just do some random numbers again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's the wrong, I just made it a new Y. I'm going to create my original Y, I'm going to call Y2 now, or Y1 or something. Call it Y2. Like that. And then I'm going to say that Y3 equals, actually I'm going to call it Y sum, equals Y plus Y2. So I'm going to create two other things here. I'm going to create a new plot. I'm going to plot, and I'm going to plot X, comma, Y, and then I'm going to do a comma, X, comma, Y2. Then I'm going to do comma, X, comma, Y3, or Y sum rather. Right, so I've got all my plots all into one thing here, and if you look on page 157 when they do, or no, 150, when did they do multiple plots? They do it somewhere, but anyway, that's just how you do it. Just one after the other, after the other, after the other, if I remember correctly. Hopefully I'm remembering correctly. But if we want to do each one of these with its own set of information, its own set of like colors, then after each one of these plots inside of the plot function, I need to put in a set of quotes and a new comma to separate it. And in those quotes, I need to tell it what I want to do. So let's make this first one, let's do a dot dash line. A dot dash line, you put in a period and a dash right there for the first thing. And let's make it blue. Well, what is the thing for blue? Probably B, but let's check just to make sure. Blue is B. Let's make it green instead. Let's use G. So and then I want it to be a star, so it has to be star next and then G. Right? So you do your line type, your point type, and your color. And then I do the next one. I go to the next one. I put in some quotes, put in another comma, and I want to do, let's say, the first thing that I choose is the line type, so I'm going to choose dotted line first. And that's going to be the colon, and then it's going to be, my points are going to be squares, so I'm going to use an S. And then I'm going to use, it is S for square, right? Yep, S for square. And then for color, I want to magenta, so I'll use M. And for the last one, I'll just let it choose the default however it wants to do it. No, I'll choose I'll go ahead and choose what I'm going to do comma, and I'm going to do my double quotes, and inside my double quotes, I'm going to do a hexagram for my, well, no, I'm going to do for my line, I'm going to do a dash line, so I do 2 dashes, and then I'm going to do a hexagram, and then I'm going to do a cyan, so I'll use C for my color. And then I go ahead and here push enter. Doesn't like that. Something wrong with my color line type argument. Somewhere I did this wrong. Let's see what I did wrong. I don't think I did it wrong. It's line type first and point type, then color. Line type, point type, then color. Yeah. Line type, point type, then color. Where's my error? Anybody see my error? Oh, this one, it's not dot dash, it's dash dot. So I have to put the dot after the dash. So previous one, and I put the dot after the dash instead of the dot before the dash. There we go. So you got to use the right symbols. And then we go to our plot. My plot window is floating around out here. And you can see that I've got all 3 of these things here. So, do all kinds of crazy stuff with this. Okay. And of course, up here with the little zoom feature, you can zoom in on this, or zoom out, zoom in, however you want to do it. You can zoom in on a particular point. Let's say we want to zoom in right here where all these 3 points are coming pretty close together. So let me do it very well. So let's do this. I'm going to zoom in just on this square where these 3 points are coming together. But there's another way to do that as well. These 3 points come together on the y-axis between 1 and 7, and on the x-axis between 3.8 and 4.2. So I can actually change my axes by going down here and typing in axis rather, and I can choose my x and y axis minimum and maximum. The first 2 numbers are going to be the minimum and maximum for x, and so that was 3 point whatever it was, between 3.8 and 4.2. So I go ahead and put that in. Do a 3.8 comma 4.2, and then the next 2 are for the y-axis, and that's between 7, what was it between? It was between 1 and, let's say, 8. So I go between 1 and 8 for the y, 1 comma 8. And it's actually expecting this to be an array, so you got to put some square brackets in there. So it's expecting this as an array. Then you hit enter, and you go back to your thing, and it'll zoom that in that particular way. So it's zoomed it into that particular point between 3.8 and 4.2 on the x-axis and 1 and 8 on the y-axis. So you can choose where you want the plot to zoom into. You could also scale the x and y axis to be exactly the same. So if we do this one, we do axis equal. It will, because normally what MATLAB does is it scales it so that the graph looks nice and you can see all the points and everything very nicely. But if you scale it equal, oh, no, sorry, I did that wrong. You don't put it in parentheses. You just do axis equal like this. Axis set as equal. Then what it does is it will scale whatever we did last. The last thing that we did, we have this scaling between 3.8 and 1 and 8. So it's going to scale them equally now so that you see 1 through 8 now on the x-axis as well as the y-axis. So that both axes have the same numbers on them, and it's showing you the same amount of the graph. Let's see, what else can we do with axis? You can add a legend. Let's add a legend to this. So if we add a legend to this graph, and all this stuff is done after you've made the graph. That's important. Now a legend, of course, is going to include text, so that we're going to want to use quotes when we put this legend in. So our legend will be, I'll put my name on it, Jared's graph. Can't use the quote in here like that because it has to be put at the end. Jared's graph, and then I can put a comma and I can put something else. Don't touch it's got to be single quotes. And I can do a comma, and I can do another one and say, or you die. Right? Now, if you want to put single quotes at Jared's and don't, you can do that, but it requires that you use LaTeX format. So I'm not going to teach you that right now. We'll learn a little bit more about that later. But let's go ahead and put a legend on and see what happens. So there's my legend. Jared's graph, don't touch or you die. And what it's done is it's labeled the green one as Jared's graph, the purple one is don't touch, and the blue one is or you die, right? So it labels each one of those. For each one of the things that you've graphed, you can put a legend up. If you put up a fourth one, I don't know what it'll do. It'll probably just give back an error. But since I had three graphs, three things to label, I could label all three of these plots within this graph on my legend. You can also put a text box in the graph just by using the text, call it text. It's not capital T, it's just text. Put a text box in the graph, but you either have to tell it where to be or it will put it somewhere automatically. So the first thing I'm going to do is just put one in there. So I'm going to just text here, we'll call it, close it, hit return. It wants me to actually tell it where to put it, so I'm going to have to tell it where to put it. And I have to tell it where on the graph to put it. So I'm going to put it at 6, 6, for example. 6, 6, text here, and then we hit return. So let's see what it does. So on the graph at 6, 6, 6, 6 right there, I put a text box in. And then there's one more thing that we can do. This one we can put in another text box called a G text box, and this allows us to move the text box around. So we just put in the stuff that we want in the box. We don't tell it where to put it. We just put it in, and it gives us a little cursor here. We can decide where to put the text, and then we put it in. So that's very useful. All right. We've already looked at labeling the axes. We've already looked at giving it a title. So we're done with that. What time is it? 12:50. I'm going to just take just a couple minutes to get a drink, and then I'll be right back, just because I'm getting a little dried out here. And then I'll be right back, and we'll do some more examples of graphing. I'm not going to do the next one because it's using a lot of math that's beyond what we expect of you in this class. But example 5.2 we might take a look at. That one's not too bad. Then we want to move on. Actually, you know what? I want to just move on because these next parts get pretty tricky. So let's skip the next two examples. They're doing the same kind of things that we're doing already, but we're going to skip now to what we call subplots and then to some different kinds of plots. I'm going to get a drink. I'll be back shortly. Okay. That's better. Excuse me. So now we're going to get into we're gonna talk about what we call subplots really quick, and then we're going to talk about some different types of plots, different ways that MATLAB can plot things. So what subplot does for you, subplot is another function. And let's actually start over here. Let's go ahead and clear my command window. Let's clear, well, we can leave most of those things there, but we can, we'll close all the figure windows. When you use the function close all, it closes all your figure windows that are open already. Subplot gives you the option of dividing the plot window or the figure window into several smaller plot windows. So if I use subplot, it's kind of like a matrix of plots. You have m number of rows and n number of columns. So if I do 1, 2 for my subplot, what did I miss? I missed something. 1, 2, 1. Return. There we go. So this one splits it into a kind of like a matrix of plots that has 1 row and 2 columns, but it only has 1 plot in it. If I do this 1, 2, is it 1, 2, 2 that I do this? Nope. So it puts the 1 plot in the first plot, in the first spot, and this puts it in the second spot, is what it does. And then, because it's only got 1, you can also do 2, 2 here, and then it'll put it in the second spot right there. But you can also do 2, 2, 3, and it'll put your window in the third spot because it goes across the rows when it's counting. You could also put it in the first spot, or whatever else. So, oops. So any subplot splits the window into multiple plots. And you can do, I don't know how many it'll allow you to do. A lot, I guess. Give you a lot of different plots. And this allows you to compare a lot of different plots all at one time in one spot, which is really quite nice. So let's go ahead and use this. I'm going to go ahead and I'm going to clear out my command window again, and I'm going to now make some plots. So let's make a subplot window 2 by 2, and in the first spot we're going to put our first plot. So that's my first command. There it is. I'm going to go back to my command window. Now my first thing that I'm going to do is x equals pi over 20. So I've got x already here. Let's do a new x, I guess. X is going to equal pi divided by 20. We're going to start at that point. No, we're going to start at 0 rather. And we're going to do, we're going to go in steps of pi over 20 up to 2 pi is what they want us to do for this example, and see how it works out. So there's my x, my new x. And I'm actually going to do this subplot. I'm going to do a different subplot now. I'm going to do a 2 there. They're going to do a 2 by 1, so it's going to have 2 rows and 1 column. So 2 plots right on top of each other, essentially, like that. And then I'm going to plot x comma sine of x. And you can put the function sine of x right inside the plot like that. That's perfectly fine. Doesn't have to be defined any other way. And then I hit return, and then I go look at my plot. So in the first position, it put my plot sine of x, and there's still an open position down here because there were 2 rows, 1 column. Now in my next one, for my next trick, I'm going to do subplot, and I'm going to actually just arrow up to that. 2, 1, 1. It's going to be the same size subplot window, but I'm going to put this next one in the second position. And the plot that I'm going to put in there is going to actually look a lot like this, but it's going to be now the sine of 2x. 2 times x. Right there. So I go ahead and look at my plot. And you can compare the sine of x with the sine of 2 times x. And if I wanted to add another one to this, I could do that, but I would have to change my subplot because I don't have room for another one. So I go up to my subplot. Instead of having 2 rows in one column, I need 3 rows in one column. And I'm going to put this next one in the third spot. And then I hit return. And now it has changed my plot window. Should have. It's changed it so there's an extra spot there. But it hasn't changed what has happened before in that window. So what it's done is it's erased what I did that's getting in the way, and so I'd have to go back and change everything to do that. So I'd have to go back up and change this one and replot it, and change this one and replot it. So you can do it, but it messes things up. So you really should know what you're doing beforehand, how many you want to do beforehand, or you have to start over. And in the command window, starting over is a pain in the neck because you have to redo every line. But if I'm doing this in an M file, it's not that hard. I just go back and change those previous lines and rerun the program, which is exactly what I want to do. So those are subplots. And of course, subplots can include multiple columns and multiple rows. You can do 3 by 3s and have multiple things side by side and everything else, and however you want to do that. So that takes us all the way through two-dimensional plots using just your normal X, Y kind of plots. But MATLAB is capable of doing much more complex things. For example, MATLAB is perfectly capable of doing polar plots. What is a polar plot? Well, a polar plot is another type of two-dimensional plot that instead of using X and Y, an axis that is going up and an axis that's going sideways, it uses X and Y and calls them theta and R, where theta is an angle and R is a radial ray. So this is what you can still use the same kind of XY axis, kind of like this, if you want to. But instead of this being X and this being Y, we're measuring angle from this axis all the way around this way, where this is 0, this is pi halves, this is pi, and so on. And if you go this way, this would be negative pi halves, and so on. Right? And then you measure from this point where these two intersect outward is your R. Okay? So this angle that goes around this way or this way is what we call theta. It's the Greek letter theta. You can call it whatever you want in MATLAB, since MATLAB doesn't care what you call things. And then we usually call this one R, of course, for the ray that goes outward. Using this system, you can plot anything that you can plot using X and Y. But the equations look very different. The equations look extremely different, in fact. Not just very different, they look way different. So, for example, let's plot something really quick using theta and R in MATLAB. Where's my MATLAB? There's my MATLAB. So I'm going to start by defining a theta. And I'm going to say that theta equals pi halves, pi divided by 2. No, let's do a different one because that's going to be kind of not obvious. Let's do pi divided by 4, which is 45 degrees, right? Pi divided by 4. So there's my theta. And I'm going to say that R equals, and I'm going to give this one an array. Actually, let's not do an array. Let's just do R equals 3. That's fine. And then let's do a polar plot, which you use polar is the command for that, or the function for that. and I'm going to do polar r comma theta. It's r first and theta second. Hit return. Go look at my figure window, and this is what it looks like. Oh great, I need to turn off all my stuff here. Let's do a clear command. Let's do close all, and then let's do this. There we go. So what did it do? Let's see, where's my point? I can't see it. It should be at 45 degrees, which is right here, and at 3, which is right there. Is that 3? It should be a point right there. Where did it go? That's 0.2, 0.54. R equals 3, pi over 4, R equals 3. R and theta. Let's choose my axis. For R, I want it to be 5. For theta, 2 pi. So let's go from 0, comma 5, 0, comma 2 times pi. Not letting me do it. I have to do it for. I have to do it differently on the polar axis, apparently. Why can't I choose that axis further out? Okay, theta and r. That's correct. Polar t sine 2t, that's fine. Oh, it's theta first and then r, that's why. They actually put in theta first and then r, not r and then theta. I thought it was r and then theta, so let's try that. So let's do theta comma r. There it is. No, it's not. It's still not there. That was a little piece of something on my screen. What is that? Don't know. So anyway, what this should have done is it should have put a point right here at 45 in r. That's a very simple graph. Maybe I'm just being too simple for it. But if this was 1, 2, and 3 out here, it should have put a point right there at 45, comma 3. And maybe it just doesn't like doing single points in polar. But let's do something else in polar. Let's do an equation in polar, for example. Let's use x and y. They're going to use x and y again here, and that's fine. X is going to equal 0 to pi over 100. So it's from 0 in steps of pi divided by 100 to pi, just pi. Okay. So there's our x. And now we're going to calculate something from x using the sine function x. We're going to just use y equals sine of x. So we've seen what this looks like in the Cartesian plane. In the Cartesian plane, this is just something that goes up and down, kind of that sine wave that we're used to, right? But let's plot now, polar plot, x and y, x comma y, and see what it gives us. That's what the sine of x looks like in polar. Kind of looks like a circle that starts at 0, at the 0, 0 point here, right? And it comes out and goes around up here to its peak. It looks very different, a lot different. Here they do something kind of fun. They do a couple of different things that are kind of fun. they create little flowers by making more of these things. Okay? Let's see here. Start with x equals, well, they're going to use r this time, and that's fine. Let's do r equals, and let's do from 0 to pi to 2 times pi this time. From 0 to 2 times pi. We're going to do in steps of pi divided by 100 again. That's going to be my r vector, and then my theta vector, which will be my y vector. Oops, that's not what I wanted to do. I'm going to call this my theta vector. No, that's not right. Sorry, I did this backwards. They called that top one theta, which makes more sense. I was reading ahead here. So let's do this. I'm trying to do the examples as much as possible like in the book so that you can follow along and use the same examples. But this one is theta equals this, and then r equals 5 times cosine 4 times theta. 5 times cosine 4 times theta. And then we're going to make a polar plot of that. Polar of r and theta. Theta and r, rather. And then we go take a look at it, and it looks like this. It looks kind of like a flower, which is kind of cool. But it turns out that you can actually make different flowers. So you can, let's put the hold on. So we're going to keep that last one on there. So let's make a different flower. And they make a different flower. It's 4 times, instead of 5 times cosine, it's 4 times cosine. So let's see what happens when we do 4 times cosine. 4 times cosine, and then instead of 4 times theta, it's 6 times theta. So let's see what these two numbers affect in the flower. Hit return, and we go back to our image. Remember, the first one comes out blue, the second one comes out reddish. So our original one, oh, then we need to plot it. So polar theta r. There we go. So let's go back to our image. Where is it? There it is. See if it comes out. There we go. So now, instead of the blue one, we get the red one. So what's different? Well, the petals don't go out as far, so the petals are smaller. Something changed the petal size to smaller, and there's more of them. Before, we had 1, 2, 3, 4, 5, 6, 7, 8. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what changed what? We went from a 5 times cosine to 4 times cosine, and we went from a 4 times theta to a 6 times theta. Well, I think the 4 times theta gave us the 8 petals, and the 6 times theta gave us the 12 petals, don't you think? And I think the 4 and the 5 determined how far out they went, how big they were. Right? And they do all kinds of other things in here. They show you how you can get one with only 2 petals and one with only one, something with only 1 petal. You can make all kinds of weird shapes that are kind of cool in these practice exercises. And then in number 5, they show you how to make a star, which is kind of cool. That one's a little more complicated and a little more difficult to understand. But let's go ahead and see if we can understand it, because it's important for your homework. I'm going to close out of this, and we're going to start over again here. Well, let's see. Yeah, we'll start over again here. We'll clear command window. Excuse me. Excuse me, sorry. I have this medicine that I take that causes me itchy throat and coughing without warning. Excuse me. Okay. Next thing is the star. So we want to, let's go ahead and clear out all of our things we've saved so far. Let's start again with a new theta. Theta is going to equal now pi over 2, pi divided by 2. We're going to start at pi over 2, and we're going to go to 4.5 pi by 4/5 pi jumps. This seems kind of weird. So we have 4/5 times pi. Those are the steps we're going to take, and then we go to 4.5 pi. 5 times pi. That seems really weird, you may think. So we're going from half pi to 4.5 pi. Remember that 4 times pi takes us around twice around the circle, right? So if we go to our unit circle idea here, this going all the way around once is 2 times pi. Going all the way around twice is 4 times pi. We're starting at half pi, which is right here. We're starting at the top right here. That's where our theta begins. We're going all the way around once, all the way around twice, and then we're ending at 4.5 pi. So we're ending at this same place because this is 4 pi and this is 4.5 pi. So we're starting at this point and we're ending at this point apparently. And we're taking steps that are 4/5 pi. Now that's the weird part. Why would we take steps that are 4/5 pi? 4/5 pi is just less than pi, right? So it's just less than pi. So 4/5 pi will get us to about right here. So the second point that we're going to go to is right here. And another 4/5 pi is going to take us all the way around to here and up a little bit to about right here. And another 4/5 pi is going to take us around all the way to here and around a little bit to about here. And then the next one is going to take us to here, and then we're going to keep going. It's going to be, and this is actually going to end up giving us the 5 points that we need to draw lines in between. So that's why they chose theta to go in these funky steps around this funky thing like this. And that's important for you to understand because that's a little trick you're going to have to learn. It's not mathematics so much as it is some geometry that you have to learn. And you have to remember that going around this circle once is 2 pi, going around at half is pi, is 1 pi, and so on and so forth. Has anybody not worked with pi and 2 pi in this class? You understand the radian measure? Have you been in trigonometry before? Not really? Is it making sense at all to you, this whole idea of the pi and the 2 pi? Okay. If it's not making sense to you when you go to do the homework, at the end of the homework for this homework, please come to me and talk to me and we'll help you out with it. But it's simpler than it sounds, but it's certainly, we certainly don't make it simple to understand, unfortunately. But anyway, we go back to MATLAB and we see if we can do this. So we've got this angle that we've created here. It's essentially 5 points, one of which repeats because you come back to the same point. And then we're going to put in 6 lines, or we're going to draw between these 5 points 6 times. Is it 6 times or 5 times? Yeah. So it's going to be 6 times. And the 6 times are going to be the six things that we're going to do are just 6 lengths, essentially. We're going to choose a length of 1, so we're going to do, we're going to make an array of 1s. So each length of our star, each side of our star is going to have a length of 1. So we need 6 of these, so we're going to do 1s, 6, and then we're going to make our plot. So our polar plot, polar, is going to be a polar of theta, and 1s ended up being answer, so we'll call it answer, right? Now let's see what it gives us. Theta and rho must be the same size. What did we just do here? Oh, I created a 6 by 6 of 1s. I don't want a 6 by 6 of 1s. I want this, let's call these sides. of the star equals, so this should be just equal to 1, 1, 1, 1, 1, 1. There we go. 1, 1, 1, 1, 1, 1. Hit enter. Then we're going to do our polar plot of theta and sides. And it makes our star for us. So what that did is it drew these lines that are each one length, essentially, that are going to go from a distance of 1 out to a distance of 1 out to a distance of 1 out, and it creates this star. You're going to do a very similar thing later, but instead of creating a star, you're going to create things like hexagons and triangles and squares. So you're going to have to change the angles that you go to, and you're going to have to change the number of ones that you have. So for example, if we make a square, we would need to go between 4 points to make a square. What 4 points would you choose if you were going between 4 points? I would go between 0, 90, 180, 270, and back to 0, wouldn't you? So I need to create an array of angles that goes from 0 to 2 pi to pi over 2. So I'm going to go by steps of pi over 2. So I'm going to go back and do this one. I'm going to create my theta, and it's going to be in steps of, I'm going to start at 0. I'm going to go in steps of pi over 2, so 1 over 2 pi. And then I'm going to go all the way around until I get back to where I started, which is 0, but I'm going to call it 2 pi, right? And instead of having ones that are 4, instead of having 6 of these ones, I'm going to need 4 of them, right? And then I'm going to go ahead and plot that again. Let's see, what did I do wrong here? Oh, because I started at 0 and went back around, I actually need to have 5 ones because they're both, because it's actually, we're going from the first point back around to the first point, so that's actually 5 points that we hit. So that one needs to be that one, and then I can do my polar, and then we'll see what happens. And that gives me a square. And you can do a similar thing to do one of the harder homework problems in here, creating hexagons and pentagons and other things. But the key is to change the number of sides to be 1 more than the number of sides on the shape that you're making, and to get the angle correct so that you're putting the angles in the right places. So, okay, that is that for polar plots. Now we're going to skip logarithmic plots again. Logarithms being a little bit beyond what we do in this class. We don't need to really work with those. But MATLAB can do other kinds of plots like bar graphs and pie charts. So let's take a look at how MATLAB can do those. Let's make an array of x's. We're doing this array here. 1, 2, 5, 4, 8. And I'm going to have a y of x from 1 to 5. So what we're doing in the second one here is we're putting x in the first row, and then in the second column, in the second row, we're going to go from 1 to 5 because there are 5 things in x. So we've made x look like this: 1, 2, 3, 4, 5 on the bottom row, but all the same numbers in the top row that we had in our original x. That's y. And then we're going to do some subplots here, and we're going to show you some different ways that we can plot this. So subplot. Do a subplot. We'll do a 2 by 2 subplot, it looks like. We'll do a 2 by 2 subplot, and we'll put this in the first one. And what we're going to plot there is going to be a bar graph. So we use bar function, bar graph, and we're going to do a bar graph of x. So it can actually just do a bar graph of the first set of variables, and that's fine. Bar graph of x, and you just do bar x, and then you can actually title it as well, just like we did before, using the title function if you want. I'm going to skip that part. But this is what a bar graph of just x looks like. There's 5 things in it, and it did a bar for each one of those 5. for the value. First value was 1, the second one was 2, the third one was 5, the fourth one was 4, and the fifth one was 8, and you're good to go. But you can also do a bar graph of y, which we will do. Bar graph of y. Let's see what that gives. Remember, y had 2 rows to it. It had a row 1 and a row 2, so let's see what difference that makes. So what it does is it puts each row in its own thing here. Now I should have put that subplot in a different one. Let's go back here. Let's put bar x in the first one. And then let's do a subplot 2, 2, 1, 2. And let's do bar y in that one. So now we have both plots on there. And then let's do another one. Let's do another subplot in the third spot. And let's do bar, what's the next one they want us to do? Oh, they want to do a 3-dimensional bar plot. So 3-dimensional bar plot of y. That's fine. Let's do a 3-dimensional bar plot of y. And that shows us 3-dimensional where they put them side by side. This is the first row. The first row is labeled here. So you have this one that's kind of wonky, and then the second one just goes 1, 2, 3, 4, 5 right up there. 3-dimensional bar plot. And you can also do a pie graph. Let's do a pie graph. They do the pie graph of x. That's fine. Oh, let's put it in, first of all, let's do a subplot. Subplot 2, 2, 3. Put it in the fourth spot. Let's do a pi of x. So we see what that looks like. There's your pie chart of x. It automatically labels it in percentages, but you can change that. There are all kinds of things you can change. You can do histograms. You can do 3-dimensional pie charts. For example, you can do pi 3 here. It gives you 3-dimensional pie chart. Or you can do a pie chart of y. See if that works for us. And it splits it into 2 different things. It puts both things into one, actually. If you do it as just a regular pie graph, you can see it a little bit better. It's a little messy there. But it gave you both of them. And you can label them and everything else just like all of the things that we've done so far, all the plots and everything we've done so far. They all get labeled the same. They can all be manipulated the same ways using the same commands. Okay. Another example before we get on to one more thing to do before we get on to 3-dimensional plotting and animation. So let's do x equals 0 to, and we'll do steps by pi over 20, and we'll go to 2 times pi, and we'll let y equal, y1 equal the sine of x. So we're going back to one that we've done before, and y2, we'll do y2 equals the exponential function, which is e to the x. Like that. And we'll do a subplot here so we can plot a couple of different things here. And we're going to do 2, comma 1, comma 1. So 2 rows, 1 column. And we're going to put this one in the first spot. And we will plot x with y1, but we'll also plot x with y2, just like that. So what happens? What we get is we get 2 plots, one that looks really flat. This looks like a flat line, this blue one. That's the first one. That's the sine. Is the sine of x. supposed to be flat? No, it's supposed to be bumpy, right? It's supposed to be, and then it has this exponential that, you know, it shows what the exponential does, but it's really kind of crazy here. This doesn't really show us what we want to see. And so what we can do is we can actually change the axes so that there's a different axis for each of the plots. One plot has one axis, the other plot has another axis, but they're still plotted on top of each other. So the way that we do this, let's see if I can do this properly. Here we go. Okay, so what we're going to do is we're going to do a new kind of plot function, which is called plot YY. So I'm going to go ahead and use this same one. I'm going to do plot YY. And what this is going to do is it's going to change the y-axis for each one of these to an appropriate axis so that you can see what's going on. Which is what plot YY does. We're going to put this into, I'm actually going to change, cut that out. And I'm going to do a subplot really quick and put this in the second one. So plot YY now looks like this. This was the original one. The second one shows you a blue axis that shows you what the blue thing is doing as it just goes between 1 and -1. But on the red axis, it goes between 0 and something to 500 once it gets up to 6 here. So you can kind of see that this one changes much more rapidly than the other one. That's your plot YY function. So two different axes on the same plot. Kind of useful. All right. Here's one more thing that I forgot to make room for. There's one other thing called a function plot. We call it f-plot. This is more like you're used to when you use your calculator or you use some other math program where you can plot a particular function over a range. You have to put in the function sine of x, but you have to put it in parentheses. You have to put it in, not parentheses, single quotes. And that tells MATLAB to kind of look up that function and see what it is. And then you can tell it where to plot it from and where to plot it to on the x-axis. But that has to be an array, so you have to put it in square brackets. And in this case, we're going to plot it from -2 times pi, and then we do a comma, and we go all the way to positive 2 times pi, just 2 times pi like that. And then you can hit enter, and you can take a look at your plot. So it's just a different way of plotting things where you don't have to enter in the values first and then plot it. It also gives, in many cases, a very smooth and a very quick way to plot something for using in MATLAB. All right, now the last two things to do are really, we have 4 sections left actually. We're in section 5.4. We have 5.4, and that takes us all the way through 3-dimensional. And then we have 5.5 and 5.6 and 5.7. But 5.5, 5.6, 5.7 are mostly about using the menu to do things with your plots. 5.5, you're actually editing plots. 5.6, you're creating plots from the workspace window. And 5.7 is saving your plots. So I'm going to concentrate mostly on 5.4, 3-dimensional plotting here for the duration of the class. It's 2:30, 1:30? 1:30. When is this class supposed to go till? 2:30? Something like that? 2:30 or... What time does this class start? 12 o'clock? No, it starts at 12 o'clock. Not 12:30. Starts at 12 o'clock. So this class starts at 12 o'clock and it goes till 2:30 technically. I don't think we've ever gone that long. But. So anyway, we'll get through this as much as we can. So Anyway, three-dimensional plotting, where we can create some more interesting stuff. We'll start off with this one here. Getting tired of sitting on my bum. So let's clear everything out again. Clear those. Okay, now, again, we're going to start with creating a array of numbers. We're going to use the linspace command to linearly space some numbers between 0 and 10 pi. So we're going to go from 0 to 10 times pi, and we want 1,000 points. So we want 1,000 linearly spaced points between 0 and 10 pi. I'm going to suppress that because it's going to be a big matrix, or a big vector. And then we're going to let y equal the cosine of this thing, cosine of x. And we're going to let z, because it's three-dimensional, we need three variables, right? So z is going to equal the sine of x. And we want to do a plot, a 3D plot, so plot 3 of x, comma y, comma z. You may be surprised by the result here. And what we're going to do is we're also going to put on the grid, So in 3D plots, the standard plot comes out like this with no lines on the graph anywhere, just like in 2D. But we can choose to turn on the grid. So we'll turn on the grid right here. And we'll label our axes too. So if I turn on the grid, it gives me the grid, but it doesn't tell me which way is x, which way is y, and which way is z here. So I'm going to actually figure it out. So let's do label. We'll do x label. So let's figure out which one is the x label. Which one is the x-axis? So I'm going to call this x, right? That's my x label. Let's go back to my plot and see which one is the x. X label, here it is, x. So the x dimension is this one going this way. Well, that makes sense because this thing is moving linearly this way and we made a linear space for our x's. The things that are moving back and forth should be the ones that are going this way, and that's where the circle is, so that makes more sense. And we'll do a y label. We'll call that y. And we'll do a z label. And we'll call that z. Turn. And we find that our y label, our z label is here and our y label is here. So those are the dimensions where the circle is existing, and then our x is out here. Put a title on it, do whatever you want to it, and whatever else. So there is our little spring here. Now I'm going to create a new one. I'm going to put a hold on this one, and I'm going to create one that's slightly different. I'm going to do hold on. So now that picture is going to stay there. We're going to try to create another one of these curly cues, but I want it to exist in a different dimension. Instead of coming out along the x-axis, I want it to go, let's see, which direction is the z-axis? The z-axis is up. I want to make one that goes up along the z-axis. How do I do that? Right, the x-axis on this one had the x equals 1 or the 0 to 2 pi. So if I change something here, let's see if we can do it. I don't know if I can, but let's see if we can. So instead of the x having the linspace, I want my z to have the linspace. So let's call this. We can still call it z if we want to, because that picture is going to stay on there. But I'm going to call it something else just to make sure that I'm not messing myself up. I'm going to call z1 equal my linspace. So I'm going to go back to the linspace, and I'm going to come out here and I call this one z1 instead of x1. And I'm going to let the others equal multiples of that. So y1, let's see, if z1 is the linspace, then x1 would be, so y1 would be the cosine, would be the sine. So this one would be y1, I think. Let's see if it works. And x would be the cosine. x1 would be the cosine, and these would be cosines of z1. And I got to go back and fix this one because it's not cosine, it's not sine of x, it's sine of z1. So let's see if we can get the 3D plot of x1, y1, z1 to do something interesting for us. All right, it's done something. Look, it goes up in the z direction. This one's going in the y direction, this one's going in the z direction. And they've both got they're both in different planes, and so but they're still there. Kind of cool. And you could do it the other way as well. Let's do something else that's interesting. Here is a cool one, comet. We're going to use our original variables x, y, and z. We'll do the comet. Let's actually close all, and then we'll do comet. So the comet is another type of plot function. Let's see here. P, X, Y, Z. Oh, sorry, not for comet. I need to do comet 3 because this is three-dimensional plot. Okay, so comet 3. There we go. Look what it does. It actually plots out, it animates it point by point. So it starts with the first points and it just moves on until it goes through the entire plot instead of just plotting it all at once. So it's your first encounter with animation. And you can do the same thing with the other ones, x1, y1, z1. I think you can do them both at once, in fact. Let's try that in a second here. So here's the one in the other dimension. It goes up instead of sideways. And this is actually going to be helpful for your homework because this is going to be something that you do in your homework. And then, let's try to do them both at once. Nope, won't let me do them both at once. Oh well. So your first animation. Now, let's move on. Last type of plotting we're going to do. And it is called surface plotting. Another three-dimensional type of plot where we're going to create surfaces. So we've already used the idea of mesh grids. And to mesh together two different things and create a big matrix from a small matrix. And we're going to use that a little bit here. And we're going to use two types of plots here called a mesh plot and a surface plot. So let's start off with, we're going to have to create a fairly large matrix here. So I'm going to use my matrix builder to create it. Z equals just an open matrix. And I'm going to come over here to my workspace and open this up. And I'm going to type in all these numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the first one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we come down here and we go to 11, no, we go 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 18, 20. In the third row, we're going to do 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So there is our matrix that we've put together. And we want to create, we want to do a mesh of Z. Let's see what happens. So it's created this mesh of Z. Essentially, as you go out in your X dimension and your Y dimension in each of these, in your Y dimension, I believe this is the Y dimension right here. If you go in your Y dimension, it separates these into your rows. So your first row is here, your second row is here, your third row is here. And your columns end out up here. There are 10 columns to each of these rows, right? And then it plots the numbers that are in those rows and columns. So row, column, number is on the Z-axis. If you just use the mesh with just 3 by 1 matrix, or 3 by whatever matrix, right? So if we wanted to make this more interesting, give it some curvature, then we would change around those numbers, because the numbers that they gave were, first of all, 1 through 10, or 0 through, no, it was 1 through 10, that's this 1 through 10 right here, and then 2 through 20, which is this one, and then the 3 through 12, which is this one. Not very exciting. So if we want to make it more exciting, we need to make that matrix bigger. So let's make that matrix bigger and give it some weird numbers. So the first one we'll leave is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The second one, instead of being 2, 4, 6, let's just type in some random numbers. 2, 3, 6, 7, 2, not 102, that would make things messy. 2, 4, 5, 3, 1, 1. And this last one, let's do 13, 11, 4, 4, 7, 7, 3, 2, 11, 10, 1. And let's see what happens. And you can see that this first line is still just very simple. It goes from 1 to 10. But the other ones start to get really wonky. And it really messes with the shape of this. We start to get some craziness. Now we've only got 3 rows. If we change the number of rows, we can change this as well. We can make it even more interesting. So let's put in some more rows. Let's just put in some random numbers. Oops. So as we start putting in more rows, and we plot this thing, we can see that we get more depth, we get some more interesting stuff going on. It starts to look more like a landscape. In case you're wondering, this is how digital animation works at a very basic level. At a very basic level, you're creating matrices that tell you how things rise and fall, how things bend and turn. And then you're plotting them in this mesh grid. This is called a mesh when you're doing digital animation. This is called the mesh grid. And you create this mesh, and then you manipulate this mesh using math. You create an equation that tells how this mesh should change if the character is going to swing their arm, or if they're going to move their head back, or if something else is going to happen. It can get really complicated. For example, let's watch a video really quick on how complicated this can get when you're doing digital animation. Has anybody seen Finding Dory? The new Dory thing. So in Finding Dory, the new Pixar, one of the newer Pixar things here, they have this. Here it is. They have this octopus. Okay. They also have a squid. So there's the octopus. Okay, so let's go one more thing here. Animating octopus. I thought they might show it there. Dory. There we go. Come on, ad, go away. I don't want to know about my T-Mobile. There we go. Ah, what just happened? Ah, I gotta watch the commercial again. Okay.
Yeah, so I'm a character supervisor. You have to engineer the puppet, basically, that the animators use to create the performance. Actually, an engineer worked on Hank for about 6 months, I think, just figuring out how to do create a new type of curve that the tentacles can use to make an octopus move around and squish and squash, yet make it specific enough that animators can grab any part of him and move correctly. It's a problem of simplifying, breaking it apart into individual pieces and putting it back together again.
Okay, so in digital animation, there are two kinds of people. There's this kind of person who has to create the character in the computer. This guy is a mathematician, scientist, a programmer, a brilliant genius, and he gets paid a lot of money. And he has a permanent job in this position. Then there are the animators as we know them as artists, as animators have always been. They've always kind of been artists rather than computer geniuses. Those guys get hired by the job for the most part. Most of those guys, when they're doing a movie, they'll say, okay, we'll hire you for a couple $1,000 to come and do this character. And then you don't have a job anymore, and you don't have health insurance, you don't have anything else. They don't get paid squat. The artists in animation anymore are just a dime a dozen. They're living on food stamps, and it's really unfortunate that the job of artist animator in Hollywood is over. It's gone. You never have a full-time job. The computer guys do it all. Because what he's going to do is he's going to create this model that an artist can just push around with a mouse. But the model will follow this mesh grid that he's going to create. Let's take a look.
This is an octopus walking on land. It's horrifying. But there's a complexity of motion here and specificity in terms of how it interacts with the ground, how it can connect at any point and move. That's hard. This is kind of what art gives us. It's kind of like a blueprint, right? So this is a really early version of Hank, and the cool thing here, What you can't see is that all of these tentacles were set up slightly differently.
So if you look really closely, which you probably can't really see really well, but if you look really closely, there's a mesh grid in here. These points are points of movement that they're going to use to move this mesh grid. And the mesh grid will follow these points using whatever parameters that they plug in. Let's count his tentacles. 1, 2, 3, 4, 5, 6, 7, 8. Over there, you can't see the other two. There's 7 and then 8 over there. There's 8 of them. Each one needs its own.
Race car, we're giving it to them to drive. So we gave them different configurations in each of these tentacles. This is a simple test of can we get that like rolling elbow or that elbow that travels down the leg that you see so much.
So that's just one movement. It's an entire program.
It's not bending like it's
thousands of lines of code.
And this was a real breakthrough test for us. You can see it's starting to have that weight and slop that a tentacle we want it to have. It's contacting, it's sticking, and then releasing. It's doing all that stuff that we were challenged to build. This was about a year after we started.
That took them a year to do that, and you could see in that one, you could see the mesh grid. See the mesh grid in that? Let's do that again.
You can see it's starting to have that.
Look at the mesh grid in there. It's all in there. This is nothing more, really, than something that we just created, but they've been able to animate it and apply some physics to it, apply some other interactions with other objects. This object up here obviously has a mesh grid to it. It's just mesh grids at the bottom end of it. And I have friends that work in both departments. I have a friend that worked at Pixar in their mesh grid department, in their computer department. He had a full-time job, got paid a ton of money. It was a lot of work and really stressful. He ended up leaving Pixar for that reason. But he went and got another job, another place, full-time job, happy as can be, and because he knows the computer stuff. My other friend has been working in Hollywood for 15 years as an artist. And he just barely got his first full-time job. It is a full-time job with Disney, but it is his first full-time job. So, I mean, it takes a long time to make it as an artist. He was working essentially freelance this whole time for the past 15 years, just picking up jobs here and there, doing what he can. And living in LA sucks. Everything about LA sucks, not just living in LA. But LA just sucks in general, but it costs like $1 million a year to live in LA. And if you're working part-time jobs, freelancing, all this crap, you're living like crap. It's not a fun place to live. It's a great place to live if you have millions of dollars, but it's terrible if you don't. And so it's kind of interesting the way that it's gone, the way that it's changed.
Weight and slop that a tentacle we want it to have. It's contacting, it's sticking, and then releasing. It's doing all that stuff that we were challenged to build. This was about a year after we started working on it, so it was a long time before we got to this point.
Our farm is in their walls alone. Baby, find this at the location. Ooh, that is good. Poor baby. Let me get that for you.
It just kind of shows the flexibility of the interface. It can squash, it can stretch, it can move around.
Each one of these mesh grids can change.
Reacts to that motion. This is a final animation.
And each part of the mesh grid is connected to another part, so it affects the other parts.
See what it looks like underneath. This is what kind of animators are manipulating all the time. Here's that shot final. And with that in mind, like you can kind of see all the screen.
So the artist animators get to move each one of these parts of the octopus, and those affect the other parts of the octopus by all of the code, all the computer code that's been written into it.
And the lighting's put into the shading, and the shading on top of the animation, and how none of us really know. And then the sim, like how they're controlling the suckers that are interacting, extra jiggle, it's just really cool. And the camouflage is really cool too. So our shading artist, he actually applied an animated textural effect all over his skin at this very kind of cellular level. I don't know if you know how camouflage is specific. Yeah.
Now, I don't think that they're going to talk about it necessarily, but this character taking more than 2 years to animate. Took them more than 2 years to get this done. It took them so long and was so difficult that they ended up only animating 7 of the tentacles in the end. In the end, they cut off one of the tentacles because they just ran out of time. they couldn't just copy one and put it on there because they all interact with each other. So we'd have to do one more tentacle, and they just ran out of time. So instead of pushing the movie back, they just changed the movie story. And in the story, we find out that this octopus got in an accident somehow with, I think, a slamming door and lost one of its tentacles. And so he only has 7 tentacles, and Dory calls him a septopus instead of an octopus, which is just kind of funny. So anyway, it's very science, it's very programming, it's very engineering, very physics, very numbers, very math, very much what we're doing. This is that, and that's where the money is really made there. It's where if you can do that part, you're really valuable, because the artist part is just point and click after that. The other part that they talk about with the colors and textures is also very much programming in computers. That's what my friend did. If any of you have seen if you've ever seen the Pirates of the Caribbean where they have the big waterfall that the ship goes over, my friend's job in that movie was to animate that waterfall, was to make sure that that waterfall looked real. And so, and that was pretty much his whole job. So it's a very interesting thing. He was a texture specialist. So that's what he did with computers. He also did fur and skin and other things in other movies. So anyway, that is kind of what we're talking about when we get to this, when we've got these mesh grids that we deal with. Ours, of course, doesn't look like an octopus, but ours is very, very simple. We could make it look like an octopus, and with this program we could even make it move like an octopus. But the programs that they use are much more suited to what they do and can do it much more efficiently. This program probably is equally powerful to that program, the program that they use, which is called RenderMan. But it's not designed specifically to do it, so it's a little more difficult to get it done. Okay, so that's the mesh plot. What about a surface plot? Can we just use the same? I think we can just use the same thing. Let's see. No, yeah, maybe. Let's see here. I don't think I can do a surface plot with this particular Z. Oh yeah, I can. So this surface plot, it just fills in all the mesh grids so that you have an actual surface to it. It gives it that surface feel, and then you can start messing with coloring the surface, texturing the surface, and doing other things. So it just fills in a two-dimensional surface in this three-dimensional space is what it does. So you can do that. If you have more and more complicated ones, you can still have surface plots, more and more values, more and more numbers in your array, and so on and so forth. And if you don't have that, if you don't have more and more, like my array is pretty big, it's a 6 by 10. If you don't want a 1,000,000 by 1,000,000, if you don't want to build a 1,000,000 by 1,000,000 thing array to make this octopus or whatever, you can start to use the mesh grid command, which is something we've used before, to build up your arrays into larger arrays to get the kind of surface that you want. So let's do this example here. X. This is actually one that we've something similar to what we've seen. Let's start with x equals an array of numbers from -2, and we'll do it in steps of 0.2, and we'll go all the way to 2, just like that. Then we'll do a y that is the same, just like that. And then we'll use the mesh grid command. If you don't remember how this is done, this was in the last chapter where we're going to create a n by n array of numbers from x and y. So we're going to use capital X and capital Y for our new row and column, or for our new arrays rather. And we're going to do a mesh grid of x and y for this. So the X's and Y's will be used to make the rows and columns of big X, big Y. Like this. Now when we hit enter here, remember that X and Y go from -2 to +2 in little steps. And we're going to create big X and big Y. Let's go see what big X and big Y are. Big X and big Y are the same ones, but you have these several rows now of these numbers from -2 to +2 in the X. And in the Y one, if we go to the Y, it'll be the same thing, the big Y, except the -2's are in the columns and they go down to +2. So we've just created this huge array of these numbers from these smaller vectors. And then we can go ahead and we can create, for example, Z. We'll create big Z, and we'll say that big Z is going to equal big X dot times the exponent. So what do we want to do? Exponent of negative big X dot to the power of dot power of 2. So we're doing x squared minus y squared in this case. So it'll be y dot power of 2. Yep, that's right. So that's going to be our z. And then we're going to go ahead and we're going to make a surface plot. Of our z. Actually, we'll do x, y, and z. Because you can do all three if you want to. X, y, and z. And you get this. So it's kind of an interesting function. Probably my favorite one would be this one, where instead of z equaling the exponent x of x squared, exponential of x squared and y squared, I would like to do 2 to the x and 2 to the y. Let's try that one. See what that does. Oh, I have to plot it now. Yeah, that one created a weird one. All right, well, anyway. So, surface plots. Surface plots. Notice that these plots are colored in specific ways. And what it is that the numbers that are at 0 are at yellow. As you go down below 0, it gets closer towards purple on the rainbow spectrum. So it goes from yellow towards purple. And then if you go up higher, it goes towards red. So it's what they call it a temperature color map. So the high above 0 is red, goes towards red, below 0 goes towards blue, and it goes in between. It just kind of morphs in between. But there are different color maps that you can use. They have a bunch of different ones listed here. And if you actually help color map, it should come up here. Yep. So it shows you all the different types of color maps you can use, and it changes how the color scheme works out. There's another kind of plot called a contour plot. Let's take a look at the contour plot. I'm going to switch back to my old XYZ. Instead of z being equal to that, z is going to be equal to this now. And we'll make a contour plot now. Contour of x, y, z. And this is what the contour plot looks like. It has the same color scheming where things that are above 0 are one color, things that are below 0 are another, but it's the same kind of thing, but it's a slightly different one. But this is looking at the plot from above, where it rises up into one and the other. So one of these is, this one here is a rising, and this one here is a lowering. So this is a mountain, this is a pit, you could think of it as. It's like a contour map. And then, what's the last one here? The last one is a surface contour combined. So you can actually see how they relate to each other. So this one's called a surf C plot. You do x, comma, y, comma, z. And this one's kind of interesting because it shows you the three-dimensional plot, the surface plot, and then it shows you the contour plot underneath, where one of them goes above the zero and this one goes below the zero. And the middle line is actually green here, between green and blue. This one. So anyway, that's what we're seeing here. Up here you can do things to edit the window, to edit the plot. You can do some colorings, you can do changing things around, moving things around. You can insert things into it, the Z labels, X, Y. This is just a faster way to do things up here. So it is possible to manipulate your plots through here using the tools, the insert button, and then these other tools down here as well, just so you know. For example, add in a legend, change the color plot, or show the color plot legend rather, do some coloring things. I mean, there's lots of things you can do up here. The last thing we're going to show you is how to create a plot from the workspace window. So we go to our workspace window over here. And I've actually never done this before. This is kind of new for me. So let me see if I can do it. I go ahead and I right click on it and I go down here to the different kinds of plots you can make with it. So I'm going to plot X, I can do a bar X, I can do an area of X. So there's an area plot of X. We didn't look at area plots because they're kind of beyond this class. If I click on Z though, it'll give me more options because Z is a bigger array, so I can do contours, surface plots, mesh plots, all kinds of different plots with this one. So I'll hit on the surface plot and it'll create the surface plot for me automatically, which is kind of nice. So you can plot directly from the workspace, and that's new to me. So great stuff right there. And that's all we got for today. That's all there is. Any questions? You good to go? All right. Have a good one. We'll see you later.